Righty. Well, there are a couple of warnings in this presentation. You'll see them when we get to them. But if you find it's all too much, you're welcome to leave. The exit is there, and counseling will be available at the end. All right. Hi, I'm Pauline. I'm an associate professor here in mechatronics and IEEE, which is, of course, part of EAIT. Is that the acronym? I've only been here a decade, so I'm not really entirely sure. Anyway, can I just get a sense of who my audience is? Y'all students? Yes, y'all students? Mechatronics students? Anyone not mechatronics? Excellent. Now is a great time to convert across to mechatronics. Brilliant. Alrighty, fantastic. I'm entirely biased, as I am the program manager for mechatronics. I will probably see most of you in my course. Who's currently in my course? Yes. Who's heard of my course? Who's survived my course? Who hasn't survived my course? Yet. Don't worry.
I actually failed the same course last year.
Oh, okay. There you go. So that makes you a silver class frequent flyer. Keep it up for another year, you'll hit gold class.
Right.
I'd say there's perks, but really there aren't. Excellent. All right, so today I'm here to talk to you about something that is near and dear in my heart, in that it's sort of part of the reason why I became an engineer. I'm going to talk to you about the tiny giant robot. Subtitle, A Different Way of Walking. Alrighty. So I'm the head of the Robotics Design Lab, which is one of the little subgroups within UQ. We're basically people who care about building robots and making them better from like a holistic design approach. And I'm also a Trust Autonomous Systems DCRC fellow. Probably means nothing to you guys, but other people are like, oh. So yeah, I'll be impressed or something. Okay. What about me? Well, I'm kind of weird. I wanted to be an engineer ever since I was 5. I didn't know what an engineer was, but I knew I wanted to be one. I wanted to be one of those people who builds cool things, who builds complex assemblies and constructions and devices. You know, all the other kids wanted to be an astronaut? I wanted to build the rocket those poor saps would have to fly in. Those fools. Yes. I've been working in drones since 2002, which seems a long time ago now, and I guess it is. But for me, that was actually during my 4th year at university. It was during my thesis project. So the work that many of you guys are doing, you for instance, who are currently my thesis monkeys, right? That actually was the start of my career in building robots. And my background's in particular on drones. So unmanned aerial vehicles, flying things, rotorcraft in particular. And I did some of the early work that people still today care about in making quad rotors robust and stable, and in particular improving their flight time and flying characteristics. I also did some of the early work in drone manipulation. You can see I have a picture up there of my postdoc work at Yale, where we were actually the first to do grasping of unstructured objects with an aerial vehicle outdoors. So if you are familiar with Amazon's delivery drones and some of Google's projects in that area, we actually got there first. We did it back in 2010. I'm also a serial entrepreneur. I've co-founded 3 startups. I have another startup on the way. And I'm sort of one of these people who's been around a long time in this space. And I have watched it grow from something where we built everything by hand. That's a $60,000 aircraft back in 2005, all the way up to building things that today are the modern equivalents that cost a fraction of what they used to be, and yet still do the same thing. So it's a fascinating project. So bipeds, very, very different from flying vehicles. Why didn't I get into bipeds? Well, the simple answer is no one was building them. I actually asked when I was looking for a thesis project when I was in undergrad at ANU, I said, cool, I want to build walking robots. And I looked around and they're like, yeah, no one builds that in Australia. It's too expensive. It's too complex and too hard. Look, maybe if you finish a PhD, you can go overseas and maybe someone will take pity on you and let you work with them. That sucks, right? And 2-legged walking machines are really interesting. I mean, they've got legs, right? Legs are cool. I have legs. You have legs for the most part. In fact, chances are very good you have an above average number of legs. Considering that wheeled robots are stuck rolling around on flat surfaces or ramps, the fact that bipeds can engage with discontinuous terrain and go places where they can't go, it's actually pretty impressive. And quadrupeds, so far as walking robots go, are relatively simple in comparison. You know, you always have 3 points of contact on the ground, you always have enough volume and space in order to balance. You never have to worry about the dynamics of a quadruped unless you're doing something fancy. So bipeds are much more challenging to build, and that makes them much more interesting. They have to balance, they have to stand upright, they are unstable, and their actuation and sensing requirements are extreme. You always have to think about what way is up. You always have to think about what you're putting your feet on. You always have to worry about, am I getting enough power in the right place at the right time to do this locomotion task? And as a consequence, for those of us who are nerds, well, it's interesting, right? It's not just more of the same. It wasn't done by Hosada back in the 60s like everything else fucking was. And the other thing is, I'm also a bit of a weirdo, and I'm a huge MechWarrior fan. Like, huge. I actually had my Battletech MechWarrior collection valued to be about $10,000 back in 2008. I had the largest collection in the southern hemisphere of such things, and if you try and quiz me on it, I will destroy you. Because I'm a nerd, right? As one of my favorite ones, and that's my dream. I want to build a giant fucking robot to crush the cause of my enemies. Who here has similar dreams? Who here doesn't have such dreams? I thought not, right? There's a joke that we used to tell in engineering circles, which is that mechanical engineers build weapons, and civil engineers build targets. We're all mechatronics engineers. We build smart weapons. Excellent. All right. That's great to talk about, but how are we actually going to do this? Now, one of the things you might say is, hasn't Boston Dynamics kind of done this? Like, why? Why bother? You know, they already have people pushing these things around and kicking them and hitting them with sticks. Yeah, I look forward to hitting mine with sticks, too. You think this is done. Like, why are we wasting our time with this? Does anyone know why this is worth doing if BDI has already done it? Any takers? You already know, yeah?
Because it's hella expensive.
Because it's hella expensive. It's fuck off expensive is what it is, right? How much does an Atlas cost? Does anyone know? No?
2.3 million?
Where do you get that number from?
My butt.
Yeah. Okay. Your butt's probably the right shape of the answer, but the thing is, I don't know either, because they won't tell you.
Huh.
They will not disclose how much it costs, but estimates are somewhere from $1 to $2 million each. Why? Because so much engineering goes into this thing. The actuators in particular are extremely capable. They have to be fast and precise and accurate and strong all at the same time. Because think about it, what's Boston Dynamics Atlas doing? He's constantly trying to put his foot in the right place at the right time, to push off with exactly the right amount of force, push him back to where he needs to be. So if he ever goes off course, he always has to make a motion to bring him back to the right place. And if he gets it wrong, if he overcompensates, well, problems. And that's an expensive thing to have go terribly wrong. So, gosh, it's difficult. And you know, there's lots and lots of applications where we would like to build shit like this without it costing the earth. Things like courier delivery, compound security, you know, walking around a shopping mall parking lot, urban patrol, wandering the streets at night, keeping it safe from people like me. You know, having these things, just wandering about, looking for cracks in the road, looking for unstable, you know, footpath geometry, or having them do something more interesting, robo-butlers. I'm sure you can imagine some other things that they could be useful for. So what do we need to do these tasks? Okay, first of all, compact bipedal stance. Yes, we could do them with quadrupeds, but we wish to go places quadrupeds cannot go. The human world is built around humans, monkeys, vertical bipedal apes that wander about on two legs in a narrow cylinder shape, sort of convex hull. And there are lots and lots of narrow, tight passageways where a human can get that, say, a horse could not. Now, a dog could probably do it, but a dog can't carry as much as a human can, even a very large dog. We also want rapid dynamic gait. You all seen things like Asimo? Who here knows what Asimo is? Anyone not know what Asimo is? Okay, Asimo is a very famous in robotic circles, Japanese robot made by Honda. And it looks like a little space-suited figure about that high, and it's famous on YouTube for falling downstairs. Quite aside from that, but it walks like that, where it puts its foot down, translates its weight, picks it up, translates its weight, and it's always stable everywhere it goes. It has this very distinctive gait as a consequence. And it looks like your grandma, because basically that's what it is. Right? That's how your grandmother walks, so that if anything goes wrong, you can just kind of stop, and you're still stable. And as a result, it's very slow. Now they're trying to make them go faster, but there's kind of a limit to what you can do with the construction and the quality of actuators that they have. Boston Dynamics started out by saying, let's make them quick, agile, dynamically stable systems. Great, except expensive. We also want our systems to be able to handle ramps and stairs and rough ground, and not just smooth, beautifully perfect, conference room interiors, right? Because you just use a freaking real robot then, right? Why would you bother? And finally, we don't want to rely on articulated arms for balance. One of the early tricks that people played with walking robots is they would basically have these flailing appendages. Right, except if you want to walk through a doorway, you can't fit with your arms all the way out. So we need something which can do all of these guys within some limits. But let's be honest, we're not really competing with BDI here. BDI, they've got the DARPA contract, right? They're the top of town. We're competing with guys like these. Nightscope. You may not have heard of Nightscope before, but you may have seen some of the hilarious internet memes that have come out as a consequence of one of their first deployments being this sort of oddly Dalek-shaped thing that immediately rolled around a shopping mall, saw reflections off the water, and thought it was a tiled surface, and rolled into a fountain. Oops, awkward. And if you search for Nightscope, these are images number 3 and 4 that come up. This is all that anyone remembers Nightscope for. So enough fooling around talking about what we're doing and why we're doing. Let's build some legged things. Legged things, how hard can it be? Well, it turns out there's a lot going on. We have friction. Hey, friction, we all love friction. It stops us sliding off the earth. Stiction, which is kind of like sliding, kind of like friction. Sliding, surface elasticity, limb kinematics, limb elasticity, limb dynamics, servo nonlinearity, force saturations, power limits, sensor noise, deflections. Gosh. Okay, actually, even before we get into things like backlash and hysteresis, there's so much going on, right? These require us to have excellent sensor models, and they require us to have excellent actuators and lots of good sensing. We need to do so much to fine-tune all of our dynamical systems models to build something that can do this dynamic balancing task. It's a ton of work, and I'm lazy. I don't want to work. Fuck that. Can we find an easier way? Now, the fact you're here and the fact I'm giving this talk and I've wasted your time with me talking like that, you probably infer that, yes, there is an easier way. If only we could decouple our locomotion from our orientation mechanics. If only we could make it so we could deal with one problem at a time. So, here's a stupid approach. I'm a drone person. I drone sometimes. I have all of this expertise that I've put together in doing orientation control, orientation regulation, flight dynamics, 6DOF orientability matrices and manifold Hermitian compact somethings. You all love Hermitian matrices, right? Yes? Are your sets compact? I know they are. Okay. What if we treat a biped like a helicopter? What if we say, okay, I'm going to worry about the orientation. I'm just going to keep the damn thing upright. And for a helicopter, we have these disturbances that enter the system. The rotor does all the orientation control by developing torques, and disturbances enter. And we reject the disturbances through control. If instead we have a biped, and we say, well, we know there'll be disturbances through the feet, but as long as they're small enough, we can play the same trick. And we'll somehow produce torques and forces in the body, and everything will be okay, right? Brilliant. Problem solved. Great. See you at coffee. No. We come back to the slide you saw before. How do we generate these forces and torques? They're magical. They rise from nowhere. How do we generate magic? Anyone know how we generate magic?
I guess would be accelerating and decelerating.
Interesting.
Magnets.
Magnets. Yes, magnets are fucking magic. Flywheels, all right. Consider a tightrope walker. Balancing on one foot. I have no contact offset with the ground, so I can't really produce torque through my feet. I have to waggle my hands. And that acts like a reaction wheel. Great. Waggle my arms, whoop, 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 and I transfer momentum between my arms moving and my body to keep my center of mass on top of my fulcrum. However, you only got so much arms that you can waggle. So we aid ourselves by having longer arms, like a balance staff. And now we can move a balance staff, it's much, much bigger, and a smaller motion gives us more momentum transfer. That's large, and it's unwieldy. And remember how I talked about flailing arms before, how people build robots with flailing arms? That's exactly the principle they're using. And the same problem applies. How many of you ever walked with a balance staff through a doorway? No, you may say that you've tried to, but you haven't actually succeeded. This is a form of reaction wheel, where we can accelerate a spinning object in order to balance things. And this is some wonderful work on a robot called Cubely by the guys at ETH Zurich. There is a voiceover, but it's boring. So here you can see they're balancing on one corner, or balancing on one edge, and they can move to the pinnacle just by accelerating and decelerating their wheels. Cameron, you know all about this one. He's basically working on a similar system for me. Work harder! Why are you here? There's work to do. All right. So it's cool. And in fact, reaction wheels are used in things like satellites. They've been used in ships. They've been used in rolling robots, wonderful robots called a gyrover, which is just this one big spinning wheel thing in it. It's cool. Things like Murata Boy and Murata Girl making unicycle and bicycle robots. Very, very neat. But why not reaction wheels? Why not just do that? Well, first of all, it's boring because it's being done. Yawn. Second of all, there are some problems. So firstly, there's only so much torque you can get out of these guys. And most of that torque is available when the reaction wheel hasn't started moving yet, what's called stall, which is great, especially if you start off at zero. But once it's moving, you have a bit of back EMF being induced by the rotation. You all know about back EMF? Anyone not know what back EMF is? It's cool. It's cool. I won't hold it against you. All right. But if you have back EMF that spins up until the back EMF itself equals the applied voltage, you're not going to get any current flow. You're not going to get any applied torque. So you can't spin any faster. You can't go anywhere. Guess what? You're stuck. And the other thing is your reaction wheels can only be made better by either increasing your applied voltage or by increasing the mass of the flywheel. Yes, you can increase the size of the flywheel, but you can only make your robot so big and still be able to call it tiny, right? So if you have a big heavy robot with a big heavy flywheel, it's going to take a ton of energy to move around. If you have a robot with a fuck off big voltage in it, well, now you have to deal with high voltages and it's a pain in the butt. That's not ideal, am I right? I'm totally right. What are we going to do? Surely there must be another way. Well, as you've probably guessed, there is. And that is my good friend, the control moment gyro, CMG for short. What if we use a high-speed spinning wheel and not accelerate the wheel in its axial direction, but actually rotate it orthogonal to its spinning axis? and use the resultant gyroscopic precession to induce torques that are useful for us. You all know what precession is? Yes, 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 no? Ah, well, I will show you precession. So the cool thing with this is that if we can use precession to do our control torques, legs don't have to do shit. In fact, our legs can be completely floppy. Behold my floppy feet. All right. And the other cool thing is, yes, you can improve the mass of your gyroscope to get better performance. You can improve the rotational inertia by moving more of that mass out towards the edge of the CMG, but you can also just spin the fucker faster. More speed equals more momentum transfer. And we can do that all the way up to the limits of the materials of the flywheel until the flywheel tears itself apart because it's rotating too fast, or until the bearings start to give out. And we spin out bearings right at the point where they become a consumable and slowly eat themselves, which is hilarious. There's a 90-degree offset, so rolling motion produces pitching torques, and pitching motion produces rolling torques. And I have a demo for you. Behold! The wheel! So if I take my wheel and I suspend it from its thing, I just kind of, oh, it's so sad. But you all were there for like high school physics class, right? This will not be a revelation for most of you. But for some of you, this is going to blow your freaking mind. It stays vertical. But you'll notice it's rotating at an angle because the weight of gravity is pulling it downwards and producing a rolling torque. And now it's slowing, oh, and gyroscopic stops, and it goes back to being level again. So it's the torque balance due to the rotating object that keeps it vertical. And now I'm spinning it in the opposite direction, and so it's precessing in the opposite direction. And if you all remember in high school physics class, if I try and turn this level with the ground, you'll see it actually kicks out sideways. That's because of that precession effect. And even if I try my absolute best to keep it level, I'm actually fighting my own strength when I try and turn it in the plane. And that's the effect we're exploiting. If you've never handled a bicycle wheel before because you lived underground in a cave or something like that, come up and play with it afterwards. You're welcome to experiment. I didn't invent the wheel, by the way. I'd like to take credit.
Not that old.
I'm not that old. I'd like to take credit, but I can't. So torque generation with a CMG. There's the well-known gyroscope equation. If you haven't seen it, don't be afraid, it's okay. It's well known for people who work with drones. It's a matrix equation. That weird little subset X is a skew vector operator. Basically, you're taking the skew symmetric vector matrix of omega there. If it doesn't mean anything to you, don't worry, come and see me, I'll explain it after. But omega here is just the axial velocities of all the components of the rotation of the rotor of your gyroscope mechanism. And the amount of torque you get out depends on 3 parameters. Thing number 1, the axial velocity. So the better your bearings are and the faster you can spin, the higher your, I hesitate to call it transconductance, but effectively your transconductance in a mechanical sense would be. Basically your ability to outsource your momentum in one axis to the other. Then you have your roll and pitch velocity applied to the gyroscope, orthogonal to the rotational axial velocity of the gyroscope, and then your rotational inertia. So your materials choice matters, as does your servo ability to turn the whole box and dice. So if you have high omega, high I, and high cross-axis omegas, then you can get away with relatively low mass for the same amount of torque generation. Why does this matter? Because if we want to build a real system, we don't want a honking big-ass gyroscope, we want something that's actually light enough for us to carry around. And humans are good at a few things. We're really, really good at building good bearings. We put a ton of effort into good bearings. We're not so good at manipulating the structure of space-time, so mass is kind of one of those things we can add or take away. We can't do much else than that. And actuators, we're okay with actuators, but we're not great. So focus on your strengths. Now, if we build our system correctly, we can get away with a tractable system. So let's aim for something small and safe to start, say around the size of a chicken. So a 1.5 kilo platform is what we targeted. We're going to need 2 actuated degrees of freedom for each leg. We need a knee, we need a hip, and we're going to need a servo in the foot in order to be able to turn on the spot. And we're going to have at least 2 servos for each axis of the CMG. Now, we don't have to have 2, but I'm lazy and I didn't want to build another bearing myself, so we just pinion between 2 servos on either side. Makes it easy. Small servos of motors, about 50 to 70 grams. We have 70 grams to budget for each, so if we sum all of our motors, let's say we get 0.56 kilograms for all of our motors all up, which is a bit under 40% of our total body weight. If we have 40% body weight for a lightweight aluminum chassis and all the fasteners and all the other bits going into it, that gives us about 10 grams left over for battery. So 10%, 150 grams left over for battery, IMU, and control circuitry, and 150 grams for flywheel. 10% mass of a flywheel. Does that seem sensible? I don't know. All right. Let's do some math on that. If we actually try and source real parts and do the designs, then we end up being a little bit under mass. We get about a 1.3 kilogram biped, which is the one we built. It's 240 millimeters tall, 150 millimeters at the hip, which is sort of the dimension that matters for scaling bipeds. And the ankles are 45 millimeters apart in the center. 156 gram gyroscope, because we save some mass, I could safely be a little bit over mass. Made from 316 stainless steel. We end up with 1.42 times 10 to the negative 4 kilogram meters squared of rotational inertia. And the gyroscope motors we've chosen give us 180 degree of travel. So we can turn our gyroscope gimbal a full 180 either direction. Right? We can spin up to 23,000 RPM using brushless DC motors to drive our gyroscope. We need to spin at least 13,000 RPM to make it stable. How do I know this? Because I spent some time doing the math, and I'll go through that in just a minute. What we actually run at is about 15,000 RPM, slightly more than what we need, just as a safety margin. It means that as our bearings start to wear down, we can still have our speed drop a little bit before we run into troubles. So if we had all of this, our knee servos would need to provide about 13 kilogram centimeters torque for mobility. Our gimbals would have to be able to source half of that, because weirdly enough, the knees always have to be able to provide twice as much as the overall torque loading on the biped itself. And that turns out to be a function of the geometry of the cantilevered knee structure. We can use basic hobby servos for this. We have some wonderful servos, the HBL 575 SLs, which are low profile servos, and I love them very, very much. I encourage you to go out, find some, cuddle them, and bring them home. They're an excellent addition to any family. They're gorgeous. Look at that. Beautiful, shiny, and chrome. And they provide you a glorious 16.8 kilogram centimeters worth of torque. Why do you care? Well, that's actually pretty honking good for a small servo like this. And in particular, a low profile servo, which doesn't take up a ton of vertical space, which is really important for packing reasons. These servos have a limit of 6.5 radians per second, but that actually works just fine for us in our design, so it's not a big deal. As I mentioned, we've got a 1.3 kilo biped. We'd like to be building an actually giant robot, but our funding is limited at this time. So we're building one the size of a chicken. Now it's worth making a note about safety here. Way back in 2004, I showed you on my slides that black thing that I built. It was a $60,000 robot. We didn't know what we were doing. We'd never built a quad rotor from scratch before. It was a 4 kilo aircraft, and it had rotors that went a third the speed of sound. Mach 0.3. You can calculate how fast that is. What I didn't tell you then is that the rotor tips were also 0.2 of a millimeter thick at the tips. They were knife edge sharp, and they were terrifying. Dangerous designs can sneak up on you. We didn't plan on building such a monstrous thing. We just sat down, did the numbers, and calculated what we needed to build. It wasn't until we turned the damn thing on we realized, we could feed a cow in one end, we could get paste out the other. This is not good, right? We didn't even think through the ramifications of what we're building. So don't let dangerous design sneak up on you. Think about the energies and velocities involved in real terms if you can. So let's do a quick calculation. E equals a half I omega squared. You should all recognize that calculation. Anyone not recognize the calculation? Yeah, I wouldn't put my hand up either. You guys are honest at least. All right, but that's the rotational energy of a rigid object rotating at omega velocity in radians per second with a rotational inertia of I. So we have 1.42 times 10 to the negative 4 kilogram meter per second, kilogram meter squared of rotational inertia spinning at 23,000 RPM. So that's about 2,400 radians per second in God's units. What does that look like in terms of energy? That's about 412 joules. That's about the same as a 9mm pistol bullet. Who would like to be shot with a 9mm pistol bullet? Come see me after. I'll sort you out. However, that seems a bit onerous when you think that if you go down just a little bit in velocity, if you have something like a 13,000 RPM one, you get 131 joules, which is about the same speed as the same energy as a cricket ball thrown at 147 kilometers per hour, which I think is like the world record for the fastest bowling pitch. I think. I'm not 100% sure on that. I don't play sports balls, so I wouldn't know. It just so happens cricket balls are approximately the same weight as our gyroscopes. Complete coincidence. But it doesn't take a big change in speed to go from shooting you with a deadly device to hitting you with a high-speed sporting implement. And these small changes actually matter. Okay, so little more than half the speed radically changes your output on how deadly something is. Now, that said, if you get fast-bowled by a cricket ball on the side of the noggin, the insides are going to be scrambled eggs, right? So still not great. Still have to care about safety, but we have to expect for the possibility that we might be shooting pistol bullets rather than cricket balls. So if you're going to build something that shoots bullets, let's make it bulletproof. And so we did exactly that. There's the adage in engineering safety of saying eliminate, substitute, isolate, separate, PPE. The hierarchy of safety. If you can eliminate the deadly, dangerous thing, do it. If you can't, substitute it with something that's less deadly, less dangerous. And if you can't do that, put it somewhere far away where it can't hurt anyone. And if you can't do that, at least keep it not touching you. And if you can't do that, well, that's what PPE is for. PPE is the last line of defense, not the first. All right? We can't eliminate or substitute, so let's go for isolate if we can. So we've built a thing, and I don't have one here with me, but I should have, which was basically a gyroscope housing made out of 6061 aluminium, which is very similar to that being used by the Bradley Armored Fighting Vehicle, which is also 1/4-inch aluminium, but with a little bit more silicon in it to make it more weldable, apparently. We didn't have to make such compromises. So this is better armor than it has. We tested that thing on a torture rig. We put it in a mechanized tilt test rig. We spun up to the maximum speed that we could get our motors to go with fresh bearings, and we ran it forward and backwards, forwards and backwards, forwards and backwards at its maximum possible cycling RPM. And it didn't fail. It didn't touch the edges. Nobody died. So at that point, we're pretty confident that we had done it right.
Does that mean your robot could take on the Bradley?
Yeah, sure. Seems about fair. I mean, you've seen the one between the chickens and the T-Rexes, right? See me after. I'll explain. All right. So we get paranoid, so we built a benched rig, and we ran the thing and ran the thing and ran the thing. Spoiler is we didn't die. But if you're going to build a thing, think about how you're going to test the thing you build as well. Also, beautiful blue anodized screws, worth investing in. Not for any technical merit, just looks cool. Great, let's build one. You probably spotted this as you came in. This is our tiny giant robot. It is roughly the size of a chicken, its actual size, albeit tiny. We'd like to build one big enough to crush the cars of my enemies. We don't have the funding yet. But, speaking of funding, as a one-off research prototype, $4,240 Australian. I don't know if you guys spend a lot of time buying robotics research equipment. You probably don't. That's laughably cheap. Most labs, if they were building a walking robot, would do their initial developmental stuff with a zero at the end. Yo.
What's the major cost of this?
Major cost is actually the servos, bizarrely enough. Well, servos and the flywheel. The flywheel that we got built for this guy is about $1,000 worth of machining. The servos are about $250 each, and there are 8 of those in this guy, so you can calculate what that comes out to. 8 times a quarter is what, $2,000?
I think I might have missed it. I wasn't really paying attention. Why exactly did the flywheel need to be so expensive? Like the material or the way it was?
Because it was precision machined, because it's going to spin at 23,000 RPM. And if you have a little bit of error in that, well, suddenly it's going to wobble and tear itself apart and fling itself away in all directions, skewer you, the ones you love. Yeah, not fun. So we put some time into getting it right. That said, when I engineered it with a safety factor of 3. So I'm pretty confident it's not going to go rogue and kill us all, and it hasn't yet. In fact, during testing, we had a software bug and the thing did a damn backflip. And the servo motors are way more powerful than they really need to be in the gyroscope. And they move way quicker than they have to. And the fun thing is, if you have the strength to walk, you actually have the strength to do a backflip. So sort of one of the comic things that walking robot developers do is they make their robots do backflips to show that they can do it. But there's nothing fancy about that energetically. The mechanics of walking required. But what happened on that occasion is that the gyroscope jammed because it moved a little bit too far and touched the side of the internal housing. There's actually a little rub mark there now. And that caused the motor driving the flywheel to actually unwind under load, and it ejected the motor out and across the lab. You had a question?
Yes, you said it was precision machined. What precision was it machined down to?
0.01
0.01
millimeters. Like, really good. Yo.
Another question is, if the energy that you would have in the flywheel at the speed that you first showed us was equivalent to a bullet firing, would you compensate for the firing of a bullet? Like, for instance, if when you shoot, there's recoil, could you add a flywheel and compensate?
The problem is at that point, your flywheel is actually coming apart. Now that energy assumes you're dumping all the energy in the flywheel into one point, which is what a bullet does. That's not going to be like that in practice. It'll actually fragment in multiple directions. And based on that knowledge, we've actually started to reduce down the safety margin of our capture system. And I'll show you what moving towards the end. So the cool shit's yet to come, and I feel sorry for the guy who just left. He's going to miss the really awesome stuff. So you can see the shape of the flywheel and how it's got this quite fancy geometry. That's there in order to keep the mechanical strength of the system as it flexes and moves. It's actually designed to have about 0.5 millimeters deflection within its environmental protection thing. The ankles are totally floppy, as I showed you. These are off-the-shelf servo motors. We're moving to prettier CAD now. We have a much nicer model for a lot of this stuff. Yo.
Why are the knees the wrong way around?
Why are your knees the wrong way around? So the interesting thing about, you and your wrong way round knees, flaunting them. The thing is, it's actually the same if it walks forward or if it walks backwards. Chickens and other creatures which actually use their tippy toes as being the contact point, sort of digigrade walking type things, have a sort of secondary knee that provides more compression sort of things. We don't care about that. The interesting thing about this is that it's actually completely irrelevant to us whether they're the right way around or the wrong way around from a dynamics perspective. Because, in fact, if you look at robots that people built in sort of the late 90s, they all walk with a slight crouch. They all walk like that. And the reason they do that is because it avoids having a singularity with a locking knee. Because from here, I can't actually move my feet directly up or down without using my hip to do it. Right? There's actually singularity, and I have to unlock my knee, then I can lift my foot. Whereas here, I don't have to. I can just keep them crouched all the time, which means I have a larger static load, but I have more dynamic flexibility and no singularity. I could just as easily make it the other way around, but then it would look weird, because it would look as if it's always walking crouched-legged, and honestly, that's kind of lame. Whereas if you build this as like an EV209, it looks like a death-dealing machine of doom, and honestly, that's what I'm in it for. I'm in it for the toys, right? Okay, so that's why. The knees are intentionally the way that they are. Other questions? All right, moving on. So how does it walk? It's easy. You just put one foot in front of the other, right? And because the gyroscope does all the hard work, simple pattern generation drives the legs. All of the computational complexity is driven in doing a very fast control loop between the orientation measurement through the IMU and the gyroscope's motion, which is a bit hard to get your head around because they're all 90 degrees out of phase. But as long as you understand that, you can just kind of disconnect the fact that your control inputs are not the direction you're measuring. It all works out. Turning is interesting though, because if you rotate the feet by some amount, by having a small angle applied each time you move, then you can just rotate the body in a pretty seamless kind of way. The robot doesn't actually have to know what's happening with respect to its leg gait generation. The foot gait and the leg gait are actually partly decoupled. Okay, so how exactly are we supposed to waggle this gyroscope anyway? I'm glad you asked. So I'm going to warn you, a bit of a hazard here. There is some maths ahead, but it's not too bad. However, I have the appropriate warning labels so you know what you're getting into. If you don't wish to be exposed to math, please leave now. All right, so we have a second order inverted pendulum model, which those of us in mechatronics probably will recognize. Basically, we say, okay, we have a foot on the ground, we are pivoting with respect to that point. We'll rock forward, we'll rock backwards. That's all right. As long as we can develop enough torque to stabilize us, we have Ix, theta double dot, Iyy, phi double dot, some applied torque, and disturbances. These disturbances are mg, the gravity pulling down on the robot, and some displacement from the contact point. This is our inverted pendulum compass model kind of thing. So all we have to do is generate TG. There's our torque control. And you know what? We know inverted pendulums are just gonna throw in PID, easy. We don't even need the integral. Not really, that would help. Okay, maybe we can put it in later. Don't stress. All right. Well, what about that V and that W? Those disturbance values. Well, every time we lift a leg, we're going to be off balance. So if I pick up my foot and start moving forward, I'm going to want to tilt forward. I know there'll be some difference between where my foot's on the ground and where my center of mass is. And if I know the kinematics between where my contact point on the ground is and where my center of mass is, I can then calculate what that disturbance will be. I should be able to feed forward that in reverse, exactly cancel it out. Haha, brilliant. And I know what my kinematic displacement will be because I'm a position-driven robot. I don't have to worry about the dynamics world that Boston Dynamics has to worry about. They don't know exactly where they are at any one point in time. That's why they have to have this fuck-off big LiDAR sticking on its head to look at the world around it and say, oh, I'm drifting, better compensate and drift the other direction. We don't care for such things. I know where I am because my leg is on the ground, and I know where that leg is relative to me because I put myself there. I'm a position control robot. I'm hardly dynamic at all. Fantastic. So as long as we can do math, And if that looks like Denevit-Hartenberg to anyone, you're not entirely wrong at all, because it's just DH. Right? Leg kinematics, throw it all in, and hey presto, we can estimate what our applied bias term is going to be. We get body angles from the IMU, we set our joint angles directly, so we can just compensate with feed forward. Nice and easy. Of course there's a catch, isn't there? Nothing is easy. Nothing is easy ever. When our gyro goes to 90 degrees, we have a saturation problem, because at that point we can't actually get any cross force. Remember, you have to rotate at 90 degrees to the direction you want to apply force in. So at this point, as I rotate, when I continue to apply torque in that direction, originally I was rotating in that direction. Now I'm applying torque in that direction, which is slightly in the plane of the ground. And at this point, it's actually entirely in the plane of the ground. And I can't apply any more torque in the direction that I need to correct in. Well, shitballs, what do? This is effectively gimbal lock. Doesn't work anymore. So we can't ever let our system get to 90 degrees. We need a way to unwind that gyroscope. So one thing we can do is simply say, well, okay, we have a biped. During one leg lift, I'm going to fall this way, and my gyroscope will move one way. During the other leg lift, I'll fall this way, and my gyroscope will go the other way. And as long as that my left leg and right leg stance face is roughly balanced out, my gyroscope is going to be going forward, backwards, forwards, backwards, forwards, backwards. And as long as they're roughly equal, it will never get too far away from the center. Seems reasonable enough. However, the world's not perfect. There is no beauty of the spheres. There's no geometric equivalence to anything. Left is not right, up is not down. There's always going to be error accumulation. This is a bitter lesson that you will all learn as control engineers, right? Nothing is perfect and everything sucks. And it's our job as engineers to take raw, unwilling, disobedient matter and bend it to our wills.
Just do pure math. The numbers should work.
Oh, pure math. Pure math. Oh, why don't we go and do arts while we're at it? No, actually, pure math totally has its place in life. And some of the very best engineers I've ever worked with have been maths engineers because they understand the music of the spheres. And they're just that little bit applied enough to bring the celestial wisdom down and make it work. In fact, my PhD professor was a maths engineering major. We started out in geography and actually geology. Started in geology and left because there wasn't enough math in it. Sick. All right, anyway. So we need a way to deal with the small accumulations of bias and momentum imbalance. So eventually we're going to have to find some way to fix this. Consequence of this is we can't hold our leg up forever. Because if I just go, nyeh, my servo will drive my thing all the way to the end, and then I can't compensate anymore and I fall over. We need a solution. All right, couple of stupid solutions we can use. Thing number one, I have a hip. I am hip with it. Hip with the kids. Sorry, there's a joke in there somewhere. I'm old. Right? If I tilt forward, I'll start to fall forward. If I tilt backwards, I'll start to fall backwards. And if my gyroscope is too far left or too far right, I could actually tilt forward and then unload my gyroscope and then tilt back. And I can do that without compromising my ability to compensate for my torque motions, because I can do it slowly. Small tilt forward, unload the gyroscope. Small tilt backwards, reload the gyroscope. That's great. What about forward backwards? What can we do? Well, it turns out that at various points in your stance phase, you have to have 2 feet on the ground. Unless you're running, in which case that's another set of problems. You always have to put one foot down to pick another foot up again. If you found a way to walk without doing that, please let me know, because that would be really handy. But during that dual stance support phase, it turns out that you describe a line between your two contact points. And if I rotate my gyroscope parallel to that line, I'll apply a torque 90 degrees out, which is directly in the line of my dual support stance. And at that point, I can unload as much torque as I want, because my servos are able to keep me on the ground, and unless my knee collapses, I can just go back to level. So if I'm off at some weird angle, and I take a step, I can tilt forward and backwards to bring myself level again. And then I can actually overcompensate until my line is parallel with my foot contact and pull myself back. So for every single step pair, I can reorient my gyroscope. Now, of course, it's harder than it looks, right? You have to do the math for it. But we call this a relaxation controller. And it turns out that there's some very, very simple ways analytically of coding them into your control system. Groovy. So, how do we do that? Let's do a control design. It looks a bit like this. I've broken it up into conveniently bite-sized pieces so you can understand what the hell I'm talking about. So remember that PD control, attitude stability. Now, this may look like a PI control to you. It looks like I. But remember, gyroscopes are controlled by the crosswise velocity. And servos on hobby servos are controlled by position. So somewhere you need to implement an integrator or a differentiator into your system. So we threw one in there, right? By the time we differentiate it, it comes back to being PD. So it's weird, we implement a PI control, but under the hood, it's actually a PD control. We do the same games with our relaxation control, which basically just allows us to integrate back out and return to zero. Groovy. Oh, and there's our feed-forward bias thing and a gate stance generator, so we can do the feed-forward control. Do some simulation, because you're not going to go and spend a bunch of money building something if you're not confident it's going to work in the simulator first. And you can see that we have something that looks sensible. That blue line on the top is our stance. So +1 means on one foot, -1 means on the other foot, 0 means no foot. Why? Because then I can just multiply the bias force by whatever the stance happens to be. That orangey color there is the orientation of the biped. So we sway about ±7 degrees. We have a little bit of a wobble during the long steps, just because we overshoot slightly. And then we come back to a constant offset when we put our foot down again. Why a constant offset? Because I haven't quite implemented that correctly. And here you can see on the bottom, this is actually the angle in degrees of our gyroscope. And you can see that the stage is going ± about 30 degrees either side, which these are numbers I like. These are numbers I can work with. Okay, that's great. But does it work? So this is a single axis test. So this is dual support stance. So both legs together, their pivot axes aligned. And you can see it's not moving very much until that weird little twitch there, and then it catches itself and it stabilizes again. We have a battery bolted on the front as a counterweight. All right. Why a counterweight? Well, we absolutely missed this at the time, but it turns out the legs don't weigh 0. I know, who knew? And these guys, these servos, being offset from the pivot, is constantly applying a backwards load. So we had to put a pivot weight on the front in order to make the forward and backwards balance work out. Yeah, I know. That's what you get if you've never built one before. So if you actually look at the measurement there, we had a very low data recording resolution because we didn't quite have things set up properly. But you can see that the values look pretty sensible, although there's that long-term accumulation of error that I warned about. And then there's this weird little glitch here. What's that weird little glitch? Turned out we actually had a problem with our driver for our IMU, where we interpreted a certain signal wrong as it crossed over a boundary. And right at the point where the thing crossed 0, it shat itself and produced a weird little glitch. And as soon as it left, it then went back to 0 again and everything worked. And this actually shows inadvertently that it has some nice disturbance rejection capability. But as you can see, we've not corrected for the error windup. So we tried it again, and this time we fixed the glitch with the 0 crossing problem, and we got a much higher resolution in data recording. And now you can see it has a quite beautiful approach in stabilization. This is the second test we ever did with stabilization. And you can see we've terminated the test there. So at this point, this is all of our published work. Right, we have longitudinal stability in the dual support stance, i.e. the easy bit. Right, this bit didn't scare me at all, and it rejects disturbances nicely. It's a mess of cables protruding from the butt end of the robot, and we really need to clean that up. They're actually a source of disturbance to the robot. And we had to redesign our control system to fit more cleanly under the center of gravity, and we added some Bluetooth in order to make data collection much easier without requiring a cable. We want to rebuild the system on a 32-bit processor, port the code across, fully refactor that code to run at 400 Hertz internally with a 100 Hertz control loop, and hopefully we'll get smooth gate generation out of that. So we're ready to start test for lateral stability with feed forward and then start taking steps. And my tired joke is making robots walk is a step-by-step process. Yeah, I know. I can hear it in your minds. All right. That's the boring bits. Let's get to the interesting bit. I must give you a warning. This is the unpublished content, so I will ask you to please not record or video what we're doing. I've asked them to stop. Did I mention it's a research prototype? It has a little safety in it, so if it goes too far, it stops moving the flywheel. And then if you bring it back up, it'll say, oh, wait, I'm level again, turn on.